Could we go over?
No.
Okay, question. Do you have an isothermal graph look like? Okay, from your point of view.
We have lots of
Like
questions.
this.
Okay,
Does that make sense?
How come I can't ask you?
Just kidding.
okay, let's just look at the big picture. Big picture. Okay? Here's pressure, here's volume, right? So, let's say that you start here. I don't care what the volume is. Let's
I'm gonna
make
just re-add them.
right?
So they're both to the fifth, right? Yeah, I feel like it just.
So, let's say that you want to make the volume bigger. So here's this syringe, okay? Here's this syringe. And it's at 5 cubic centimeters. So what's one thing that I can do to make the volume get bigger? Physically, what could I do? What's one option?
Hold back on the
Yeah, I grab a hold of the back of the syringe and I pull. Okay? It's an option. So here's the deal. If that's the case, when I pull that back, am I doing work? Yes. Okay? I'm doing work because of the fact that I'm exerting the force through a distance. Right? Okay. Now, in this case, I'm the one physically doing it. I'm grabbing hold of this thing and I'm pulling it back. I'm doing the work. Okay? Now, the other option is that I could take this syringe and I could dump it into a hot water bath. And I could have thermal energy flow into the system. Now, as long as that plunger can move, that's going to be a key thing. As long as that plunger can move, as I dump thermal energy into it, then what's going to happen is that these little molecules of nitrogen and oxygen are going to get more and more and more kinetic energy. And they're going to start flipping out. And the syringe goes, wow, you're hitting a lot harder. Okay? Therefore, we'll make the volume get bigger. So it would be analogous to, I teach a second grade class, God forbid, and they're all normal. And then I leave the room for 5 minutes, somebody sneaks in and gives them all an individual bag of like 5 pounds of M&Ms, and they all consume the 5 pounds of M&Ms. Okay? I come back in and they have flipped out. I'm going, I can't handle this. We're going to move down to the gymnasium because you all have too much kinetic energy to remain trapped within this room. Okay? So those are the two situations. So when you look at work, okay, here's your general guidelines with work. Work is either positive, work is either negative. Okay? And that's the first thing that you have to figure out is when is work positive and when is work negative. So here's the deal. Let's say that I'm going to start here, and we'll start with the simpler one. And we're going to go across like this, right? So if it's a horizontal line, what type of process is it? Is it either isothermal, isovolumetric, or isobaric? Isobaric, because what are you holding constant? Pressure. Okay, so this is going to be a certain pressure, okay? I don't know, 100,000 newtons per square meter. Okay? Whatever it is. So, as long as I maintain a constant pressure, so here's what's happening. Because it's a horizontal line, I can use the idea that work equals negative P delta V. I can only use that if it's a horizontal line. Because all I'm basically doing is finding the area of this rectangle. Here's my pressure. That's the width of my triangle. That's the height. My change in volume is this dimension. That's it. So I got a height times a width. That's it. Now here's the significance of this negative value. So I'm going to have negative 100,000, whatever that pressure is, times my final volume, which is going to be, let's say, 0.5, okay, cubic meters, minus my initial volume of 0.1 cubic meters. So right away, what's the sign of my value of W? Positive or negative? Negative. So negative work is going to be, this is significant. This is going to be negative work. So here's the deal. Anytime volume gets bigger, what's the sign of work?
Negative.
Negative. Now here's what you have to understand. In this situation, and you'll see why this works later on. I'm going to dump energy into the system. I'm not physically going to grab a hold of this thing. But what I am going to do is I'm going to dump energy in. And because of the fact that there is this atmospheric pressure pushing down against it, it has to push against that atmospheric pressure. Because atmospheric pressure pushing around on all sides doesn't want to expand. The atmospheric pressure wants to hold this thing in place. So you have to work against it. Okay? That's important. So it's going to cost us energy. So anytime you're going to do work to make something bigger, it costs you energy. Okay? So imagine that you're wrapped up in saran wrap and you start to flip out and you go, oh, this is bad. Okay? And you want to make your volume bigger. That's going to cost you energy. Your amount of internal energy that you have is going to go down because you're going to try and rage against the saran wrap and make your volume bigger. Okay? Makes sense. Cool with this. Now, implied with every point on here, implied that there's a third dimension of temperature. So this is going to be a certain temperature. And I can find the actual temperature if I knew the pressure, I knew the volume, and I knew the number of moles. I could find the temperature if I wanted to. I don't need to, but I could. So here's the question. As I go over to here, one of two things is going to happen to the temperature. Either the temperature is going to change or the temperature is going to remain constant. One of two things can happen. That's it. So, grilled cheese. What's going to happen to the temperature as I go across? It's either going to stay the same or it's going to change. Get bigger, get smaller.
How would you know?
I don't have a famous clue. That's why I'm asking. Actually, I do.
Yeah.
Look. Does PV equal nRT?
Yes.
Yeah. So when I go across from here to here, what happens to the pressure?
Constant.
Nothing. Why? Because it's less than bare. Does the volume get bigger?
Yes.
So when I get over here, I've got the same pressure, but a bigger volume. What happens to the number of moles?
Same.
What happens to R?
Same.
So what's the only way I can produce a bigger volume?
Bigger temperature.
Yeah.
Bigger.
So I got nR times a bigger temperature. So if this is T naught, this final temperature here has to be bigger. So what I've done is that I've put this thing into a hot water bath. I've dumped thermal energy into it. Now, here's what's different about this. If you have a pot of water, let's say you're in college, you want to make some macaroni and cheese. Okay, which should probably be a staple of your diet at some point without ramen noodles. And you go, hey, I want to make some ramen noodles. Well, what are you going to have to do with the water? Boil it. You have to dump energy into it. Now, do you think the water's volume is going to expand very much?
No.
No, it's basically going to stay the same. It will technically get a little bit less dense, but not enough to worry about. Okay? So, when you look at this idea, that delta U equals Q plus W, okay, there are certain equations you have to view every system through the prism. And this is one of them. You have to view this relationship through the prism of delta U equaling Q plus W, and then delta U also equals 3/2 nR delta T. Okay, these are the two prisms you have to view this thing through. So here's the deal. When I go across like this, if I'm just boiling water, you put that pot of water on the stove, what's going to happen to the temperature? Better go up, okay? You're heating this thing up. You want these little particles of water to have more and more and more kinetic energy. But I'm not changing the volume. So if my volume doesn't change, I don't do any work. So all I'm doing is dumping energy into the system to change the internal energy of the water molecules. That's all I'm doing. I'm just dumping a ton of energy into the system. I'm not, and none of that energy is doing work because the gas, the water isn't a gas. Now, if I have something that's a gas that can expand, and I can allow that system to expand, then in this situation, I'm going to have a value of negative W. So in this situation, going across, I'm going to have a negative W. But what's the sign of delta U? Positive or negative? Mr. Bugby? Or is it 0? No, man.
Isothermal. This is isobaric, big guy.
Look, what's happening to the temperature as you go across?
So is that 15?
The temperature's going up, right? So, Bugby. So if my temperature is going up, what's the sign of my delta T? So what's the sign of my delta U? So therefore, this delta U is also going to be a positive number, right? So this is going to be some positive number. I can calculate it. I don't want to. All I'm going to look at is the big idea. So here's the deal. I'm dumping energy into the system. What's the sign of W? That's going to be a negative number, right? So I want to end up with a positive number for delta U. And I know this is positive because I increased the temperature. I know W is negative because the volume is getting bigger. So here's the $1 million question. What's the sign of Q? Positive, but it also has to be bigger than W. So here's the deal. So this positive Q here has to be bigger than that W right there so that I end up with a positive delta U. So in this situation, it would be like, I'm going to leave Kendra $10,000 in my will, but she only has to spend $3,000 of it to do work. She can keep the balance, okay? So she's going to get more money than what she has to spend in doing work. So it's like, Kendra, you keep the extra $7,000, okay? If you can sleep with yourself at night, that's fine. You know, if you have a clear conscience and you're actually keeping $7,000 and not helping the children, that's fine. But that's an option for her, okay? Now, compare that, and this is where you've got to compare these things. Compare that with if I start with the exact same thing here, and I'm going to bring it down like this. Now, if you have a curved line, that's going to be isothermal. So what's going to stay the same? Temperature is. Okay? Temperature is going to stay the same. So as soon as temperature stays the same, Hallie, what's my value of delta U?
0.
Why?
Because everything's going to be multiplied by 0. So the temperature doesn't change.
Beautiful. I don't care how many moles I have. It doesn't make any difference. Okay? My delta U is going to be 0. So, but here's the deal. When I go across like this, what's the sign of my work? Positive or negative?
Negative.
Negative. So that means the Q has to be the same as the work so that I end up with a delta U of 0. So here's what has to happen. How this physically plays out is this. Okay? Here's how this physically plays out. I would dump some energy into this syringe. Okay? Heat it up a little bit. But what has to happen then is that I have to give that system time for those particles that now have all of this energy. They're going, oh, we got to do something with this. We have energy. I know. Let's push against the syringe. So they're going to take that energy, however much energy I dump into it, 5 joules, 10 joules, it doesn't make any difference. However much thermal energy I dump into it, that's how much work is going to be done. So all of the energy that I dump in goes to do work. Now, that isn't true here. I dump in more energy than what I use to do work. So this is why the temperature goes up. So I'm going to dump in 10 joules, let's say, but only but a small percentage of that is actually going to go to do work. Most of it's going to raise the temperature. Now, you have to look at what you can measure in this system. Okay? We talk about delta U. We never directly measure delta U. We can't measure it. I can't add up all of the individual particles and their collective energies. I can't do it. Okay? It is physically impossible to actually calculate delta U. But look at what you can measure. Oh, okay, I can measure temperature. Oh, that's easy, right? You've been able to measure temperature since second grade. Probably didn't in second grade think about it as the kinetic energy of the particles that are striking the material, but that's what you think of it now. So I can measure temperature, I can measure volume, and I can measure pressure. So we measure three macroscopic things: temperature, volume, and pressure. We use that then to determine what's happening with you. Okay? So I promise you, if you go to the internet, don't try and look for devices that measure delta U. It's not there. Okay? We cannot directly measure delta U. But we measure the impact of everything else to make that happen. Okay? Yes?
So, how is work negative when it's going right? What makes it negative?
When it's going in this direction?
Yeah.
Okay. When you look at this idea that you have this is going to be your final volume minus your initial volume. Okay? So in this case, I'm going to go from 0.1 to 0.5. Right? So
you're just
I'm taking 0.5 minus 0.1
okay.
times the negative pressure.
Okay.
That's the significance of that negative sign out front.
Only in an isobaric.
Yes, because I can't do it with this. Okay? I can't use this on an isothermal because the pressure changes.
Okay, so, but you can still have a negative work on those.
Oh yeah.
Okay.
But then, with this one, if I'm doing an isothermal, work is going to equal nRT natural log of VI over VF, right? So, here's the deal. And look, you have to understand why these equations work when they do. I can use this equation on an isothermal because the temperature is staying constant. Okay? But I can't use it on this line because the temperature is changing. Okay, so you have to know when to use each one. Okay? Now, if you have a graph and you just have a vertical line like this, here's pressure, here's volume. Okay? So, what's happening to the pressure? Okay, so I'm decreasing my pressure. So as I go down, if you look at PV equals nRT, I'm making the pressure smaller. What's happening to my volume? It's constant. Okay? So I have the same N on the same R, so what has to happen to my temperature? The temperature has to decrease. Okay? So in this situation, physically what would happen is this. This is the only one where you have a container whose volume can't change. Okay? So this would be like a sealed box or a steel container. Every other one's, the temperature can change. Okay? Or the volume can change, excuse me. On all the other ones, the volume can change. This is the only one where you have a completely sealed system, where the volume cannot change. So, basically, if you look at this, delta U equals Q plus W. In this one, what's the value of work?
0.
Why? There's no change in volume. There's no area underneath the line. Okay? There's nothing. So this one's simple. Okay? So delta U is going to equal Q. So to get delta U, what you want to do here is go 3/2 nR delta T. So you can find the temperature up here, then you can find the temperature down here. Now, so,
How would you find the temperature?
you just have to go temperature out of this equals PV over nR. You'd have to know the pressure here,
You have to know the number of moles.
and the volume and the number of moles. Now, but here's the bigger picture.
But you're only using machine, or delta U equals Q, or equals 3 halves R, change in speed because you don't have work, right?
Yeah.
If you have work, you think.
Yeah, but there is no work, so that's the only reason we just have.
What would be the other way to do that?
If you had work,
Yeah, then I'd have to worry just.
delta U equals Q.
The pressure is constant.
Okay, so here's the big idea. When I go from here to here, what's gonna happen? So let's say this is at, I'm just gonna make up a number. Let's say this is at 300 Kelvin. I come down here, it's 200 Kelvin. What's the sign of my delta T? I'm gonna go from 300 Kelvin down to 200 Kelvin. What's the sign of delta T? Negative. So I'm gonna have a negative change in temperature there, so therefore I'm gonna have a delta U, so that means the Q is gonna be, so which direction is energy gonna flow? Yeah. So I would take this, lock it in place, dunk it into a container of cold water. The water, the temperature would flow out. I'm not gonna change the volume. So to get this new point, I would just measure the temperature of the gas that's inside of it. I'd know the same number of moles, I'd have the same R. Now, if I reverse it and go up here, what's gonna happen? Which direction is energy gonna flow?
In.
Yeah, because then I'm gonna have a positive delta U, so I have to have a positive Q.
So I was thinking about this while at work.
Okay?
Is that how they get chemicals inside of canisters to be cold?
What do you mean?
Like, the chemicals inside of it are colder than air temperature. Is that how they do it? They lower the, I don't know.
Oh yeah,
Pressure.
you
They
just have
lower
to
the
play the
pressure.
pressure and volume game.
You can't use this equation.
Okay, Patty Brown.
Yeah, 16B.
16B. Okay, well, let's talk about 16A first, because you can't talk about 16B until you look at all of 16. Okay? So you got 101,300 pascals, which is normal atmospheric pressure. Okay, everybody says, wow, that's a lot of pressure. That's what you're under right now. Don't flip out. That's 1 atmosphere. Don't flip out. That's, we're cool. Okay? So during the process, 5.023 joules of energy is added to the gas and volume changes from 10 to 18.2. So visualize this, okay? So here's this, and it's a pretty big container, because to have that many cubic meters would be pretty big, okay? So maybe it's a plunger, you know, this is like a big, like elephant-sized plunger, okay? So here's the deal. Visualize what's happening, right? During the process, I'm going to add this much energy. So is energy going to flow in, or is energy going to flow out? In. Okay? So the energy is going to flow into the system. I'm going to put it in a water bath. I'm going to set it out in the sun. Put it in a microwave. Something. I am going to do something to increase the kinetic energy of these particles. Right? Okay. Now, you're told that the volume changes from 10 cubic meters to 18.2, right? So is the volume getting bigger, or is the volume getting smaller? Getting bigger. So here's what's happening. It's like I've given Kendra a lot of money. And I don't know necessarily what Kendra is doing with the money, but I can look and say, wow, the space around Kendra is getting bigger. So that means she's taking some of this money and she's doing something good with it. She's just not holding on to the money, right? She's taking some of this money and she's making the volume get bigger, okay? Now, so if you look at work equaling negative P delta V, what's the sign of delta V? Positive or negative? Positive. So that means the work is going to be a negative number. So we're taking some of this energy and we're using it to do work. Okay? Now, it would be possible for this volume to get smaller, right? So in other words, think about this. We're heating this stuff up, and at the same time we're making the volume smaller. What do you think is going to happen to the temperature inside of here? Would it go up or would it go down? Well, think about this. Think of that gas piston, you know, when I pushed it down and we ignited that little bit of cotton, okay? I pushed that down and we ignited the cotton. What's the only way that we could ignite that cotton? Is if the internal temperature did what? Got really, really hot. So just by pushing this down, look, delta U equals negative P delta V. So when I push this down, look at this. When I push that down very, very rapidly, what was the sign of my delta V?
You were decreasing the volume, so it would increase.
So my final
positive
volume
work.
is going to be less than my,
It was positive work.
okay,
Positive.
okay. When I push that plunger down, okay, what's the sign of delta V? Positive or negative?
Negative.
Negative. 'cause you have
Negative,
positive.
because we're going to take like 0.1 minus 0.5, right?
Positive.
Okay? So my delta V is going to be a negative number. Multiplied by negative pressure means that I do
Positive work.
positive work. Oh, I do positive work. So delta U equals Q plus W. When I did that, what do you think the value of Q is?
Negative. Positive.
0.
0. Q is 0. Because I'm not heating it up or cooling it down. Right? So there is no Q. So if I've got a positive W, delta U has to be a positive number. Now, delta U also equals 3/2 NR delta T. So if I have a positive delta U, I have to have a positive delta T, which is why the cotton caught fire.
I thought he was wanting me to say something.
No.
And that's why?
Okay. No. So, when I look at this, here's the deal. I'm dumping energy into the system, right? So we're taking some of that energy and we're doing work. So at this point, I have to do two things. I have to worry about a Q and I have to worry about W. So since the volume is getting bigger, W is going to be positive or negative? Negative. Q is going to be positive. So delta U is going to equal Q plus W. So here's what could happen. If Q is the same as W, what's going to be my sign of delta U? Or will there be anything for delta U? It would just be 0, which means the temperature wouldn't change. Okay? If Q is bigger than W, in other words, if I dump more energy in than the work that I do, delta U is going to be,
Negative.
if I dump more energy in than the work that I do,
Positive.
delta U is going to be positive, the temperature should go up. Okay? If I do more work than what I put into it, delta U is going to be negative and the temperature is going to drop. Okay? So when you look at this, the only thing that we can measure is the change in temperature and the volume and the pressure. Those are the only things we can physically measure. There is not an instrument in the world that measures delta U. Okay? So here's the anomaly of thermodynamics. We spend a lot of time talking about delta U and we can't measure it. Can't.
So what you're saying is if somebody were to create a device to measure it, they would be very wealthy.
But it's physically impossible to measure.
Kyle.
Challenge accepted.
There you go. And if when
My
you do
life's
that,
work.
remember your physics teacher who gave you the challenge.
All right.
Okay,
Because
Told you you couldn't do
delta.
it.
so your
Because
answer
W is
to
positive,
number
volume is
16A should be a pretty big negative number times 10 to the 5th.
A B is a bigger number, right?
Oh, heck yeah.
Oh, heck yeah.
Yeah. Yeah.
It should be like positive.
Still confused.
A should be a pretty big negative number. Okay?
You said because pressure increase, right?
Then on B it says the change in internal energy, right? So all you're trying to find is delta U. Do you have the value of Q? Yes, you just found the value of W. So the only thing that you're gonna have to do 16B is just add the two numbers together.
You should get times 10 to the 6th.
Yes.
Probably the 5.
What Burkett, don't insult our intelligence on this.
Oh my god, I feel so dumb.
Come on, everybody knows that.
Every time they say something, I feel like,
Come out of the way.
You have to be eternal.
Come out.
That's fine.
Yeah. Now, on number 8, your overall answer on number 8, when you get done, okay? And don't make me guess what you've done. Show me each one of those. Your answer should start with a 3 and should be something times 10 to the 6th joules.
Yeah.
again, another thing, I had all the numbers right, so then I just, okay, I had all the numbers right, I just didn't add them together, right?
No, you were using the wrong speed.
Yeah, you did use the wrong supposed to.
No, I ended up, no,
Unless you changed it.
I added them all up right. Well, like when I went back and added it, I got that number.
You used the same specific
No, I went, you know, yesterday I
did.
actually went and watched the video. That's how I was thinking, it helps.
I did, I got the right answer, so.
Yeah.
Hey, I helped you last night, Cole. Don't.
I made my best homework I've had.
17. Just one of them out of 17. All of it.
17?
I'm sorry.
Isn't it like,
Don't ask for help then next time.
No, don't worry, I'll still be asking.
What day is it?
God dang.
December or November?
Start here. What's it gonna do? Matt,
Huh.
you have 1 liter, let's talk about 17.
Oh, thank you.
You have 1 liter of air is with constant pressure until the volume is 0.5 liters. So if this is 1 liter, what's it gonna do? At a constant pressure, it's either gonna go left or it's gonna go right. Boom,
Right there.
0.5 liters, right?
Okay.
That's it. Now what are you gonna do?
why'd you draw a line up?
Doing a swing thing down.
Straight line?
No, swing.
A swinging line.
It's gonna like.
curvature.
So we had to draw the line, okay.
No, I was just showing that.
Yeah, I've never seen this board before in this class, in your little pins.
Did you buy this on your own? Did you have to ask for this like personally?
Oh, I did.
So what they say when you go outside, they're like, anything for you.
Probably like, yeah, probably since it's the hardest class you can take in the district.
Oh, hardest class.
What?
Can you go over 15C? Because I'm hearing multiple different.
Oh, you're killing me.
I'm sorry.
Slowly.
What?
I haven't seen the same one.
Okay, let's talk about words on number 15. So let's just kind of out loud. I'm just going to read what I wrote out loud. Okay? An ideal gas expands isothermally, right? So I'm going to go on like this. It expands.
How do you say it?
Okay? Expands.
This is the source heat, so the temperature.
So then when you get to 15C, did the volume increase, decrease, or stay the same?
But is it because it said like temperature was
Well, that's one option. Or you realize because it expands, you have to have negative work.
My work is. Oh yeah, my work is positive. What the heck? I don't know.
Hold on, but my work was positive.
Yeah. Wait, just kidding. Hold on. I'm looking.
I have 15 B's.
I have a positive work, I'm not feeling it.
It is,
It just
okay,
gives you the work, and the work is positive though.
okay. So when you have positive work, what does it do? Is work positive or negative?
Apparently it's positive. I did not have
Hold
positive
on.
work.
Look, what do you want on 15B?
Heat absorbed.
You want the value of Q,
Yeah.
right? 15B doesn't ask about the value of work.
Yeah.
15B asks about the value of energy,
Yeah.
right?
It's negative. Yeah.
Okay, so you're performing 3.40 times 10 to the 5th joules of work. because it's getting bigger, is the work positive or negative? All I've done is given you the number, okay? You have to decide if it's positive or negative. Is the volume getting bigger?
Yes.
It costs you energy, so the work is negative. So Q has to be positive. So you're going to dump this energy in, and then the system's going to take this energy, and then it's going to make the volume bigger.
if work is positive or negative.
Right?
But it just says like the work
So is work
All I
supposed to
do
be
is give you the number.
positive?
Okay? All I'm telling you is that that's the value of work.
I just want to know what the answer is.
So it's
Yeah, B is positive.
Yeah, so B would be positive.
Yes.
Okay.
B would be positive.
I thought that's a negative,
I
which
thought
is
you
where
were
I
giving
was
us the
making
sign, so I was
mistakes.
confused.
And then it has.
Yes,
the
the work is negative, but Q has to be
Positive.
so if
I just didn't
Okay,
get the
don't
whole
get
you
mad
were
at me
giving
here.
us the sign thing.
Oh, I
didn't
would
get that.
never do
so if
that.
the work
Hold on.
is negative, but it
So how do you make
expands,
that?
how's that work?
Because you're pushing against the
Just change
atmospheric
sign.
pressure that's trying to
So you can
hold
just
it
choose
down.
whatever you want.
Okay, like when I go to blow up that balloon, I have
So
to
because
push
work is
against the
negative-
atmospheric pressure that's trying to keep that.
So you're doing negative work when you blow up that balloon.
Yes.
So how do we
The
know when this
volume
is negative
increase.
work or positive
I don't have a number.
based off that?
If the volume is getting bigger,
The work is negative.
work is negative. There's no exceptions.
Got it.
No exception.
Because
I
it's
didn't even
costing you energy. Now, here's a simple way that you can understand this process, okay?
Doing 17.
Now, when work is done, it costs you thermal energy. Here's the simplest way to do this. Put your hand in front of your mouth, okay? And blow on your hand with your mouth completely open like this. How does it feel? It feels hot, okay? Now, do the same thing, but pucker your lips and then blow on your hand,
Oh my gosh, what? I've never thought about that before.
okay? It feels cold, because here's the deal. You're compressing the gas, right? As it goes between your lips, you're compressing the gas. Once it gets past your lips, what does it do? It expands. To expand costs it energy. And so therefore it feels cooler, which is how we have air conditioning. The compressors in your car's air conditioning system take a gas and compress it. It goes through an expansion valve, and guess what? It expands. As it expands, it cools. As it cools, you pass the air that's going to be blowing into your car over that system. You get cool air.
Oh my gosh, life just makes so much more sense. Like, oh, I've never thought about that before. That's one of those, that's a good thing.
Okay.
That's a good,
If you've ever had like a can of compressed air that you use to blow off your computer, okay?
it's really cool.
Yes, same reason.
Yeah.
Hey, physics is blowing my mind.
You know, I was wondering how my air conditioner, like in my car worked the other day, or like my heater, so that just like,
Now the heater is simple. It's just taking your excess heat from your engine and
Yeah.
blowing it over that heat.
but the
sink.
like cooling, I was like, I wonder how that happens, because I'm not a car person, so.
There you go.
There you
Now
go.
you know.
Now I've
This
got
is
it.
why it's called the air conditioner compressor. So when your air conditioner goes out, one of two things has happened. Either the compressor itself has gone bad, or if you get low on the freon, which is the gas. Okay? So if that gets too low, there's not enough to compress and expand, and it quits working.
That's so cool. I feel like I get life.
Okay.
I'm gonna go home and be like,
That was-
you know how car air
Okay.
conditioners
Anything
break
else?
to add? Right there. I'm literally gonna make everybody move when I do that. Like,
On 1A, because you're only about 25% efficient, your 1A should be around 250.
And B would be.
And your B is around 1,500-ish.
Okay.
on what B? 1B.
Make sure on 9
I got 1.4.
that I know exactly if everything's positive or negative. So what you should see on 9, obviously you should have the same number of positive numbers as you have negative values. Not necessarily numbers, but signs. Should have 3 positives and 3 negatives.
Cool. I'm sorry.
Woo!
It's just mind blowing.
Which is also why, like when you open up a can of pop with like the old lid stuff,
Yes.
you'll see a vapor because as you open it up, that gas that's trapped inside expands and it cools, and then it condenses the water vapor that's around it.
Life. It's just
Life now makes sense.
Yes, it's just life. One of those other life lessons.
Okay, so here's the last big topic. Okay? Now, this is a situation that you've dealt with, but you probably haven't given it much thought. And this is what's called the buoyant force. Now, we've talked about buoyant force before, back when we were doing net forces. Remember, I took the cute little balloon, right? And we hung different weights from it till it would just hover, right? We talked about the buoyant force, okay? Now we're going to actually figure out what creates the buoyant force. Okay. Oh, this is easy.
Hey, we talked about this in meteorology.
Okay, this is John. Look, it's John. Okay, it's John. Let's be honest. Okay, so here's the only thing that you have to remember about the buoyant force. And if you keep one thing in mind, it's simple. The buoyant force is the weight of the fluid that's displaced. Okay? Literally. If you just remember that, everything else will take care of itself. Okay? That's it. Now, but there's a couple of leaps of faith that you have to take. First off, you have to think of the fluid. Everybody thinks the fluid is being like water or liquid mercury or something like that. Air is a fluid. Okay? It is. Air is a fluid. The particles just aren't held together very tightly. So if I move my hand like this, I can feel that interaction with the air. Just like if I take my hand, I move it underwater, I get the exact same sensation, only it's stronger because of the fact that the water is more dense. So air is just a really, 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 really low density fluid. Okay, and that's okay. So the other thing to understand density is, to understand buoyancy forces, is you have to understand this concept of density. Density is mass divided by volume.
Too much.
Now, in chemistry, that's grams per cubic centimeter. In physics, it's going to be something completely different. It's the same idea. But in physics, we use cubic meters, or excuse me, mass, kilograms per cubic meter. So if you look on that chart that has all your thermodynamic data, down here towards this table 10.1, here's what you're going to be dealing here. These are the density charts that you're going to have. And yes, you will have this on your equations or on the test. You will have all of this. Now, notice that all of these are like 10 to the third. Liquids and solids, the only ones that aren't are air, helium, carbon dioxide, okay? Those are the ones that are pretty low density. But they all have some density. So air has a density. Not very much, but it has a density. So the density of air is 1.29, and that actually changes depending upon temperature. So like, obviously if the air gets really, really warm, the density goes down. If it's really, really cold, the air is more dense. So that's why, like, if you want to ride a hot air balloon typically take off in the morning because the air is cooler, so the air is more dense. So it's easier to get those balloons up in the air. Las Vegas, for example, when it gets really, really hot in the summertime, in the afternoon, they will shut down the Las Vegas airport because the density of the air has dropped so much that the planes can't take off because they can't get enough volume of air moving over their wings to create enough lift. So that value changes depending upon where you're at. Now, one of the things that you will see that's going to be important, on the liquids, you notice that water is 1.00 times 10 to the third. They use water as the benchmark value. All the metric system is based upon water. So for example, they took 1 cubic centimeter, they filled that up with water, and they said, oh, we're going to make that 1 gram. So that's how 1 gram became 1 gram. Is that they took a cubic centimeter, which is about the end of your pinky, they filled that up with water, and they said, oh, okay, boom, that's going to be 1 gram. The beauty of that, why that system works, is because at the time, you had science being done in the United States, in Europe, and all around the world. So you wanted something standard. Well, water at 4 degrees Celsius is something that everybody could standardize, and so that's why that was chosen. Now, if you look down below, when you look at seawater, notice that seawater or ocean water or salt water, whatever you want to think of it, is a little bit more dense. Okay, so that's going to be important when we do some of these calculations. Is that ocean water, if you're in the oceans, that water is slightly more dense than it is in fresh water. So if you've ever gone swimming in the ocean, it's actually easier to swim in the ocean than it is in fresh water because that salt water, which means it's a little bit more dense. Okay? So when you look at this, that density is mass divided by volume. Here's the most common manipulation you would do of this. What you would do most often is take density times volume to get mass. Okay? It's going to be the most common thing that you will do with this. Density times volume is going to equal mass. So, here's a simple thing. Let's say that I've got this balloon filled with hydrogen, and then I've got this balloon that I just blew up. Okay? So, that one sinks, that one goes up. Okay? Now, here's what you want to look at. Are they both displacing a fluid? Yes. What's the fluid that they're displacing? Air. So, if these two balloons have the same volume, okay? Both have the same volume. So, here's the hydrogen balloon. Here's the air balloon. Okay? They both have the same volume.
Is it really hydrogen or is it helium?
No, it's hydrogen.
Oh, it's not helium.
If you accepted it, it'd make your voice.
No, hydrogen, it would maybe a little bit nothing like helium. Okay, so here's the deal.
Does that flow faster than helium?
Yeah, it does. Goes up a little bit smaller.
And the reason we don't use that for balloons is because they explode.
Yeah, they're pretty frail.
Oh,
We can
are we gonna blow it up today?
We'll see the time.
We made him do that.
Okay, now, here's the deal. So I've got this balloon right here. So, what two forces are acting on this balloon?
Gravity.
Gravity is trying to keep it down, right?
Yeah.
What's lifting it up?
Buoyancy.
Buoyancy force. So which one obviously is bigger?
The point.
Buoyancy force is, right? So because it's going to go up.
Look at
Now,
that nice balloon.
if I take this balloon, okay, what two forces are acting on it? Gravity and the buoyant force. But if I let go of this one,
Oh my gosh.
Gravity overcomes.
Dude, you have something wrong with you.
Yeah.
okay, so on this one, gravity is bigger than the buoyant force, right? Okay? Now, there's a couple of different ways you can do this even within a liquid. So, within this bottle, I've got what they call, it's a Cartesian diver. It's the top of a pipette with a piece of metal that I've glued on the bottom of it. So, even if you look at this situation, right? So, this thing is floating. So, what are the two forces acting on that pipette?
Buoyancy.
Gravity and your buoyant force, right? Now, at this point, okay, is it sinking?
No.
Is it going up? So those two forces at this point are what?
Equal.
Equal. So the buoyant force is equal to my gravitational field. Neither one of this is true, so that's why this one goes up and that's why this one sinks. Now, if I squeeze this, do a little magic, okay, little sleight of hand, okay?
Wish I could see it.
Oh, I
Oh,
see.
it sinks.
Okay?
Whoa.
Wow.
Then if I go just right,
Oh, wow.
I can make it
Why is that?
hover, right? Now, if you notice what happens when I give this thing a squeeze, what you'll notice is that the level of water inside the pipette goes up by just a little bit, okay? So when that level goes up, what happens to the overall density of the Cartesian diver inside?
Goes up.
It goes up. Therefore, it has a little bit more mass. Therefore, the gravitational force becomes a little bit bigger, and it sinks. Okay? Now, I'm not changing the overall volume of the system, so I'm not changing the buoyant force. So the only thing I can manipulate is the gravitational force. So as I put more water in there, the gravitational force is going to become a little bit bigger, and it sinks. Now, when I let go of it, when it's at the bottom, that water flows back out, which is bigger. Buoyant force. So if I go like this, makes it sink. When I let go of it, goes back up, which is how submarines work. Okay? It's the same basic idea. If you're on a submarine and you want to submerge, guess what? You want to dump water into that submarine, so that then, instead of being neutrally buoyant, that submarine goes down. Now, you want to come back up, what are you going to do?
Let your water out.
Yeah, you're going to flow the ballast, you're going to force air into the ballast tanks. Submarine's going to come back up. Okay?
Physics.
Well, I
man.
love physics.
This is a good day.
It's a good
This is a
day.
good day.
If we light that balloon on fire, it will be.
Yeah,
Okay.
if we could explode that balloon. then-
Right now, let's do it with the math.
No, we will later. I just don't, I need it for now.
We only had like 30 minutes, 25 minutes. No, 20 minutes.
Used in hydrogen.
Really existed until like the 1980s.
No, they just probably just let out.
Okay, now. Now, this is where thought has to occur. Okay? I know. I want to find the gravitational pull acting down on the hydrogen balloon. Okay? Now, obviously, I have the balloon itself, right? But what else do I have in here? Hydrogen gas, right? So, my gravitational pull at the end of the day is going to be mg, right? That's going to be it. Since you walked into this room the very first day, this is how we found the gravitational pull, right? And we know g at this point, because we know the mass of the Earth and all that good stuff, we know that's 9.8 meters per second squared. Now, let's talk mass here. We really can't measure the mass of the hydrogen. It's pretty small, right? But if you look at the idea that density is mass divided by volume. If I know the density of the air, or the hydrogen, and I know the volume of the balloon, I can determine the... So instead of m, I'm going to put
It's a D, isn't it? There's no way. It's
rho
a D.
v g.
Density.
So,
Roe v. Wade.
no. So this isn't P, okay, this is the Greek letter rho. So this is rho v g.
Rho?
Now look, if this is going to produce units of force, what do I have to get out of it? Newtons, right? So density is going to be in what?
Kilogram meters cubed.
Kilograms per cubic meter, right? Times the volume in. What am I left with? Kilograms times g gets me newtons.
Wait, what?
Okay?
You find the density.
Okay.
How do you find volume?
This is going to be rho, which is going to be my density. True?
Yeah.
To give you the volume?
The kilograms
Per cubic meter, right? True?
Yep.
I got a volume in,
Meters cubed.
and then g is in.
Meters per second squared. So kilogram per meter.
So is the density a constant number based on what
Yeah,
like
you
substance
have
it
to
is?
give that number.
And then the volume you give us.
Yes.
This time.
Yeah.
Okay.
Okay? Cool with this?
I guess.
Now, what this is going to get me, okay, and this is going to be important. This Fg equaling rho Vg, this is the gravitational pull that's acting down. Now, this is the density of hydrogen. This is not the density of the air that's around it. This is the density of the hydrogen. This is the volume of the balloon, and then you have G. So, listen to me. My gravitational pull is not the density of air. Okay? It's not it. It's the density of whatever is inside. So, if you consider, let's say, Hank has roughly about the same volume. Pretend Hank is the exact same volume. Okay? Obviously, when I draw Hank, right?
Scared me.
Now, so if Hank has the exact same volume, this would be the volume of Hank times G. Why is the gravitational pull on Hank so much bigger? Yeah, he's got a lot of density. Okay? There's a lot of material packed inside of here. So with all that material packed inside of there, there's a large gravitational pull acting down. Okay? Now, so if I want to calculate the buoyant force, right? Listen to me, listen to me, listen to me. My buoyant force is going to equal the density of the air that I'm displacing. If this was water, if this balloon was underwater, I'd use the density of water. So this is the density of whatever the fluid is that you're displacing. Now, this is going to be the same volume of the balloon times G. Okay? So, if this buoyant force is going to be bigger than Fg, which is going to be the density of the hydrogen, times the volume of the balloon, times G. This hydrogen balloon, when I let go of it, what does it do?
Go up.
It goes up. So which one of these is bigger?
Buoyant force.
Buoyant force is bigger than your gravitational force acting down.
Wow.
So, look. So if I take FB minus FG, I get, if you want to define up as being a positive number, right? So what do you know about the density of air compared to the density of hydrogen?
It's denser,
The air is more dense. So therefore, the buoyant force is
bigger.
bigger. Therefore, the hydrogen balloon goes up.
Okay, so on the buoyancy one, for the density, you use this, like, what's around,
Yes.
not what the actual, what's inside
It's
of it.
not what's inside.
And then on
This is counterintuitive to what you youngins have been told. That's always inside that counts. No.
Okay.
This is about what happens on the outside.
Okay. On
the
This is
outside
the
that counts.
vanity equation.
Okay.
This is the warm fuzzy, oh, it's what's inside that counts.
For
Okay?
FG.
This is what the world around you thinks. Okay?
I'm gonna
So
forget
this
that.
is the cruel world. This is, oh, you're in second grader. Oh, it's what's inside that
But
counts.
buoyancy just sounds like a nicer word. Like,
Okay.
I feel like buoyancy would be the word.
Okay. Now, has anybody been at the pool and tried to hold like a beach ball underneath water?
Yes.
Doesn't work.
It doesn't work. Why?
Because it needs to add water.
Because the buoyant force is larger.
Okay.
Because
Oh my
water's denser than
God.
Yes.
air.
So if you try and put this thing underwater, I'm not going to change the volume of the balloon. Actually, you will, but we will leave that out of it. But what's going to happen to, instead of using the density of air, I would use the density of
Water.
So therefore, the buoyant force would go
Uh,
way up with the same gravitational pull. Therefore, you get a bigger net force. Therefore, it goes doink. Okay, which is undetectable. Okay, now let's talk. Where'd mother balloon go? There it is.
hey, do you know how your car just
Now.
stopped? You pushed your foot on the brake, which then triggered this. You were actually accelerating
Oh.
while you were He's decelerating.
Now I take this balloon
Alone.
and I drop it. Okay, what happens? It sinks. Why? Now, here's the odds. Here's what I want you to look
But they're
at.
both filled with air,
No,
right?
no, this is filled with hydrogen.
No, but that's filled with air, and then it air's around.
That's true, but there's also the balloon itself.
So the mass pushes the.
Now, think about this. Which do you think is more, what do you think has a higher density? The air inside of here or the air around it?
Inside.
Inside for sure.
So this air inside is more dense
Yep.
and it has the balloon itself,
Yep.
okay?
Okay.
But here's what's important. If I take this balloon and this balloon, okay? If they have the same volume, listen to me very carefully before you answer this question. This balloon has the same volume as this balloon does. Okay? Got that? Got this. Now, which one has the greater buoyant force? The air-filled balloon or the hydrogen-filled balloon, or do they have the same buoyant force?
The same.
Same. Why?
Because they're both displacing air.
Yes. This calculation in buoyant force, because it's the density of the air, is the same as long as these two balloons have the exact same volume. The buoyant force is the same. This balloon sinks.
So in the
Why?
Bigger FG.
It has a bigger FG, which means this density, the overall density, has to be
Greater.
greater.
So if two things have the same volume no matter what they are,
Huh?
if two things have the same volume no matter what they are, they have the same buoyant force?
If Hank here has the same volume, okay? When I drop Hank, okay, the exact same buoyant force is acting on that balloon. Now,
If
when
they have
you
the same.
stand on a bathroom scale, are you all displacing a fluid right now? Yes, you are displacing a fluid. There is a certain amount of buoyant force acting on you, okay? Because you're displacing air. So if you were to stand on a bathroom scale, I don't recommend this, okay? And you're in a vacuum, okay, I don't recommend this. But what do you think is going to happen to the reading on the scale? Is it going to go up or is it going to go down?
There's not gonna be one.
It would be less.
Well, let's come back here. So here's what I've got. I've got a chunk of aluminum suspended by a scale that's reading right now roughly about 2.5 newtons. Pretty close, okay? So right now, what's the fluid that's being displaced by the block? Air. So if I know the volume of that fluid, if I can measure its dimensions, right? Multiply that by the density of the air, I could find the buoyant force that's acting up, right? So here's what I'm going to do. I'm going to begin to add water to this beaker, okay? I'm going to fill it about halfway full. What do you think is going to happen to the reading on this scale? One of three things could happen. As I add the water, reading on the scale could go down. In other words, it could in effect be weighing more. It could go to like 2.6, 2.7, something like that. It could become less, okay, meaning that there's some upward force acting, or gravity isn't changing because it's still the same aluminum block and the scale is going to stay the same.
More.
So, how many think the reading on the scale will go up to maybe 2.6 or 2.7? 1, 2, 3. Okay? How many vote that the reading on the scale is just going to stay the same? Nobody's biting on that one? Everybody else thinks the reading on the scale is going to do what? Become less. Okay? So let's see what happens.
Watch this.
Ooh.
Pretty cool.
What happened to the reading?
It went up.
Well, the marker went up, right? But the scale is now reading 2.4 newtons. It was reading about 2.55, now it's reading about 2.4.
Oh, okay, I know.
Okay? So here's the question. Has gravity gotten weaker?
No.
No. But by displacing that air with that by displacing air with water, what do you know about the density of water relative to the density of air? Okay?
Funny guy.
That was not fist pump worthy.
Yeah.
Okay? No. So, here's the deal. So what's happened to the buoyant force? The buoyant force has gone bigger. But what's happened to my gravitational pull?
Nothing.
Stayed the same. Nothing's changed there. Now, if I completely submerge it,
Does it float?
now we're down to about 2.2 newtons. So I went from 2.55 down to 2.2. So let's just say 2.5 to 2.2. So what's the value of the buoyant force? 0.3. Because everything, right, we're not accelerating. Everything still has to add up to equal to 0. True? So I've still got a 2.5 Newton force acting down. But now my upward force is only 2.2, right? So therefore, my buoyant force is going to be 0.3. Okay? Now,
So water is more dense than air.
yes.
Okay, got it.
Okay.
Yeah.
Now, if I poured out the water, and let's say I filled it in with something even more dense than water, okay, like liquid mercury,
Very,
then what would happen to the reading on the scale?
go more up.
Yeah. So that's what I'm saying. So imagine that we're going to go to a swimming pool, and we're going to take Bugby, and we're going to have him stand on the scale before he gets in the pool. Let's say it's what, 180 pounds, to make the math easy. Let's say it's 180. Then we're going to take that same bathroom scale and we're going to put it underneath the water, and then we're going to have Bugby stand on the scale, but he's submerged up to about here. What's going to happen to the reading on the bathroom scale?
Gonna go down like 170.
Yeah, maybe 170, 175, something like that. But the reading is going to go down because now that water is providing a buoyant force. So right now, there is a certain amount of buoyant force acting on all of you. So if I jump down from this table, there is a little bit of buoyant force that's acting upward. Enough to really make any difference?
No.
No. Okay? Now, in a swimming pool, you all generally float. Why?
Because you have air.
Well, and overall, your density is less than that of water. So if we were on average more dense than water, guess what? We could never swim because we would always sink no matter what we did. Yes, otherwise known as drowning.
I've been in the pool of Martini.
Okay, got it? Good? Back we go.
Rise up.